All right, so the next piece that we're going to add is we're going to talk about waves. And so the idea here is, what is a wave? Well, up until now, basically we've transferred energy by transferring matter. So something has moved from point A to point B that has taken energy with it. Well, a wave is a means of transferring energy from one point to another without transferring matter. So what happens in a wave is I'm able to send energy through a medium, and the way I send it through a medium is through the wave. So mechanical waves are one of two types, right? So in sort of the most fundamental level, mechanical waves are the types of waves that need a medium of particles to travel through. And so these are most of the things we think of as waves. So water waves, sound waves, seismic waves traveling through the earth after an earthquake, shock waves in the air when you hear a sonic boom, waves on a string. All those have a medium. So water waves travel through water, sound waves travel through air, seismic wave travels through the earth, etc. That medium is required. Basically, how the particles within that medium interact with each other is how that energy is going to be transported without the individual particles themselves needing to go from point A to point B. Electromagnetic waves, the second type of wave, and the kind of wave that you'll deal with in 222, they do not need a material medium to travel through. So these are waves that can travel through a vacuum. And basically this is what's known as electromagnetic radiation. So the various types of waves in the electromagnetic spectrum are our examples for electromagnetic waves. So visible light is the one we know best, but all the way from low energy radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of these are just different types of electromagnetic waves, which means that they don't need a medium to travel through. Now, so we said with our definition for a mechanical wave that it's a disturbance. And so there's two ways that we could sort of deal with this disturbance. The first is kind of simulated in these top series of picture here. So notice that I've got someone holding a string. So clearly I'm going to send a wave through a string. So the string here is my medium. And the fact that each piece of the string is connected to the next piece is how I'm able to send energy without sending matter. So notice that as this hand goes up and down, right, as it goes up and down once, what I do is I send basically what's known as a wave pulse. So it's just a single sort of crest of a wave. And you notice that the rope doesn't travel from here to there. Instead, what travels is basically the pulse. So as I pull up and then down, and then that pulls the next piece and pulls the next piece. And so what you see this pulse travel across the wave. So this is our energy is being transported, right? I did work on the rope here. That the work I did is energy. That energy is being transported as it moves down the rope. So that energy is being transported through the wave without the matter itself being transported. So the rope still basically stays where it is. If, on the other hand, basically I keep oscillating my hand up and down, so if the disturbance is an oscillating source, then I have a continuous wave. So this is the idea behind a mechanical wave, right? I've got a disturbance, maybe it's a wave pulse, maybe it's a continuous wave, but it's going to transport energy through a medium. So there are three types of mechanical waves that we can talk about. So the first is a transverse wave, and the idea behind these three types is how did the particles move relative to the wave? So for a transverse wave, what I have is the particles are going to bounce up and down while the wave travels to the right. So this was the example that we just saw on the previous page of the wave traveling through the string. This is the same idea. So as this particular particle goes up, it's got to pull everything else with it. It's going to pull this one up. It's going to start to come back down. That'll pull this one back down. As this one went up, it pulled that one up. As it starts to come back down, it's going to pull this one back down. And so that's how our wave travels through the medium. For a transverse wave, the disturbance, how I move the individual particles, is perpendicular to the direction the wave travels. So the wave travels to the right, but all the particles here bounce up and down. And so that creates a wave that looks like this. Right? So the wavelength of a wave is the distance to go from basically crest to crest, or you could go from trough to trough, right? It's the same distance. But the wavelength basically tells you how long, what distance, right? How long in distance is it for a single wave? The amplitude tells you the maximum displacement. So the amplitude sort of what's the maximum height of your wave above the center line. Second type of wave I can have is a longitudinal wave. And so for a longitudinal wave, the particles bounce back and forth along the wave direction. So longitudinal wave, your particles are moving along the direction of the wave. So here for longitudinal waves, the disturbance is along the line of motion. So instead of bouncing up and down as my wave goes to the right, they're bouncing left and right as my wave goes to the right. And so here, again, we still have a wavelength. The wavelength goes from basically how long does it take for the wave to repeat itself. But instead of having crests or peaks and troughs, what I have are compressions and rarefactions. So the compressions are the places where things squeeze together. The rarefactions are where things are spaced out. And this is the kind of wave that I have with a sound wave. So sound is actually a longitudinal wave as it travels through a medium. The last one, and we just sort of bring up because it happens to be the wave that we sort of know best, probably. But when we think of waves water waves are actually neither longitudinal nor transverse. They actually have this basically circular motion as the material circles around. And so it moves a little bit to the right and a little bit up and down. And so you actually have a surface wave where you have sort of a combination of up and down and left-right motion, and in fact it's circling around. So we won't do much with this one and just sort of bring it up as a, again, because when we tend to think of waves, our most immediate example is actually thinking about waves within water. So the speed of a wave. Well, one of the things that's very nice about waves is that they travel at constant speed, which means it's pretty easy to calculate, because anything traveling at constant speed, I can just take the distance it's traveled and divide it by the time it took to do it. So one way that I can calculate the wave speed is be given information about how far the wave traveled in some time. For a wave in particular, I know that the distance that I sort of care most about with a wave happens to be the wavelength, right? That's the distance it takes to complete one wave. The time I care most about is the period of oscillation. That's the time to complete one oscillation. So when I think about the distance over time for a wave, if I think about the distance for one cycle over the time for one cycle, that gives me the wavelength divided by the period. And again, the 1 over the period I know is the frequency. So the second way that we'll tend to talk about the speed of a wave is to think about it as frequency times wavelength. So when we one of the things that we'll focus on with waves is the wave speed. So how far does it travel in a certain amount of time, and then how that relates to the frequency and wavelength of a particular wave. So you'll notice one thing to emphasize, as a general rule, the speed of the wave depends only on the medium. So for any non-dispersive waves, which is what we'll deal with this semester, right, the speed of the wave is set by the medium. And so what that means is when you start changing, say, the frequency of oscillation, the frequency at which your disturbance oscillates to cause the wave, you're actually going to change the wavelength. Right? So these two things are inversely related to each other, and the speed of the wave is basically set by that medium.